Let's begin. Good morning, everybody. Before we start continuing the lecture, let me make several announcements. First of all, we are going to conclude the section of the lecture on radiation physics today. And I have prepared a little quiz for concluding that. And I hope you can see that here. So, I'm logged in here as the responsible for the lecture, so of course I see it. I hope you see it too. There is here an entry called online tests. If you click on that.
I think only you can click on that in the administration, right? But it's there, I saw it this morning.
You did see it? Okay. The test looks like this. It asks 5 relatively simple questions on what we discussed in this section on radiation physics so far. The test will be open from 9:55 today until 10:10 today. That's a quarter of an hour. That's in the middle of the lecture. That should be enough. The result of the test doesn't enter anywhere. It's completely harmless. It's for you to see where you stand, and it's for me to see where you stand. All right, I will return to that before the break begins, hopefully before 9:55. All right. Another thing I wanted to say, we had a colleague at the Institute for Theoretical Physics, Bertolt Stech, who passed away just about a year ago after having remained scientifically active and productive until he was 93 years old. So there will be a memorial colloquium later today at 4:15 in the large lecture hall of Philosophers Walk 12. And there will be 2 colleagues speaking, Günter Dosch, who is one of our retired colleagues, about the person Bertolt Stech and theory in Heidelberg, and Matthias Neubert, who was one of the PhD students of Bertolt Stech, about fascinating by the unimaginable, exploring the strange world of elementary particles, a tribute to the science of Bertolt Stech. Maybe you're interested, and you see here, there is tea. There is tea from 4 p.m. All right, that was the second announcement. And then let me briefly speak about the menu for this week. So this is the table of contents of that book on theoretical astrophysics that we use as a basis. And we are going to conclude very quickly today, section 2.8. where I just wanted to add a few sentences about the line profile that we discussed last time and about the consequences that this has for the analysis of spectral lines. This will largely happen on the screen and not on the board. Then I would like to start the section of the lecture on hydrodynamics. So we will then jump to section 3.1 of the lecture here. We will skip over 3.2. Well, if I'm very lucky today, I'm going to conclude 3.1. We'll jump over 3.2. That requires general relativity. And we will then move on to 3.3, probably or hopefully on Wednesday. So much for the program. Now let me briefly summarize what we said last time about radiative quantum transitions. First of all, we derived a general formula for radiative quantum transitions. Let me briefly repeat that. So that was a formula for the cross-section of a radiative quantum transitions. That was 4 pi square REC, some numbers, then we had the oscillator strength. That was this number that characterized the transition probability between an initial state n and a final state m of a quantum mechanical system. Could be an atom, could be an ion. And then we saw, okay, under ideal conditions, there is a delta distribution that describes the shape of the spectral line. I showed you how to calculate these oscillator strengths. I gave you a Python notebook, for example, that showed that these numbers, f and m, are typically of order 0.1 or 1. Right? So these are relatively intuitive numbers. And then we spent the rest of the lecture to talk about the line profile function. And we replaced this by the function phi of omega that described the frequency dependence of the spectral line much more accurately than the delta distribution. The reason is that, the reason why we have to replace the line profile is that the transition energy between the excited state and the de-excited state is not infinitely sharp. There is an uncertainty relation between the lifetime of an excited state and the energy that connects it to the ground state from which it was excited. And I told you there's a rate of spontaneous decay of the excited state that comes from vacuum fluctuations of the electromagnetic field in the atom or the ion itself. There is a further process that limits the lifetime of the excited state. This comes from the collisions between atoms or ions that reset the phase of the quantum mechanical systems and therefore limit their lifetime. And those decays, either spontaneous or caused by collisions, give rise to a Lorentzian line profile. We derived that, right? A line profile that has power law wings. And since the wings are of power law shape and not of exponential shape, the wings are very broad. Right? And then we saw, okay, in addition, we have to take into account that the atoms that emit those spectral lines usually will be moving with respect to us. That gives rise to a Doppler broadening. And if the velocity distribution of the atoms or ions is Gaussian, as you expect in thermal equilibrium, then the resulting line function in total will be the convolution of the Lorentzian that you have from the finite lifetime of the excited state and the Gaussian that you have from the thermal motion of the atoms or ions. This convolution has a name. It's called the Vogt profile. And this Vogt profile I've now added to the Jupyter notebook for the lecture. So there is a little more description about this, and you can then display it and play with it. Are there questions so far? There were lots of assumptions going into this calculation. As part of the quiz, they will reappear. All right. So first of all, here's the Vogt profile. I see it. Sorry, I should have showed this earlier. So here is a somewhat more general description of the Vogt profile itself. Generally, it's defined as the convolution of a Gaussian with a Lorentzian. Both of them, the Gaussian and the Lorentzian, are centered here, and then the convolution is written down, and you see the general form of the so-called Vogt function. That's this function v. This has a much broader meaning in certain applications of mathematics. There are two types of Vogt functions, and so on and so forth. But what we need is this one. All right, if you want to have a look at it, and you look at it in a linear representation, it looks perfectly harmless. Right, well, okay. Suppose now you make a log plot. So a linear logarithmic plot. not like that, but like that, then you very clearly see the Gaussian core of the profile function and the Lorentzian wings. And this is important for what we are going to discuss now. So you see, as you go far away from the center of the line, you see this 1 over frequency square decay of the Lorentzian profile. And here in the center, you see that the line acquires a Gaussian shape. This is characteristic, and this is how spectral lines typically look, provided the Doppler broadening is caused by thermal motion. All right, now let's see what consequence this has for the spectrum that we see. So, suppose there's light with an intensity I coming along at frequency omega, and it's passing through a small geometric path length dx. It's passing through a gas that consists of n things, right? Atoms, ions, what have you, which all have a cross-section sigma of omega like this. Then the intensity is going to be reduced in this way here. Right, so the change of the intensity, first of all, is proportional to the intensity itself. Just think of the light passing through a filter that randomly picks out photons and throws them away. Right, and the probability for this to happen is n times sigma of omega times dx. And this gives you the proportionality constant for the change of the intensity with respect to the intensity. So you have the change of a quantity proportional to the negative quantity itself, which means that there is an exponential behind. Right? Whenever the change of something is proportional to something, then you have an exponential change. So as the light is passing through a finite path length, the I of omega is going to be reduced by what is called the optical depth. And the optical depth is the geometrical path length, which I now call L. So dx was a small part of L. L is the geometrical extent of the gas that is passed through, times n times sigma of omega. So you see the whole thing, the whole quantity is dimensionless. So I can meaningfully insert it into the exponential. And what it tells you is that in addition to the geometrical path length L, there's an optical path length L, which tells you by how much the intensity of passing light is reduced. All right, that's the definition of the optical depth. Now, suppose you have a spectrum. So here is some measure of frequency, and here is the intensity of omega. Then you might see something like this. Now, the width of these spectral lines is characterized by a quantity called the equivalent width, which is defined as the fractional change of the intensity across the spectral line. I'm leaving out the boundaries here. What I mean is you integrate over the spectral line. This could be broad, this could be narrow. In any case, you have to make sure that you catch the entire spectral line, which is not possible, right? Because the Lorentzian never drops, or the Fock profile never drops to zero. So in principle, you have to integrate relatively far in order to catch the entire spectral line. But then, of course, you are very likely to catch the next spectral line. Life is not ideal. So in total, the equivalent width is given by this quantity here, by this integral over 1 minus exponential to the power of minus t, of minus t, the optical depth. And this quantity I wanted to show you because it has a very characteristic shape. So that's what it looks like. That's what it looks like. Now, what I'm showing here is this quantity here, so the equivalent width, as a function of different widths of the Lorentzian profile. Right? It's scaled to the width of the Gaussian, but then I still have the width of the Lorentzian rings free. And then you see this very characteristic shape of this curve. And I'm scaling this here, or I'm showing this here as a function of a quantity tau 0, and the quantity tau 0 is everything multiplying the Vogt profile here. Right? So at this point here, when I write down the optical depth, L times n times sigma of omega, this is L times n times all of that until I arrive phi, and then I insert here the Vogt profile. And everything that goes out front, the Vogt profile, I call tau 0. Right? This is the quantity characterizing both the number density of the absorbers and the oscillator strength, of course, and the geometrical width of the gas distribution that I'm imagining. All right, now you see, this curve has a very characteristic shape. First of all, you see, if I go by a factor of 10 in tau 0, I go by a factor of 10 in the equivalent width. So I have a linear rise at first. This is obvious, right? This has to be the case. Because if the optical depth is low, then I can approximate the exponential here as 1 minus tau. So then I just have the integral over tau. And that just grows linear with tau 0, right? Because tau 0 just multiplies the optical depth. Okay, fine. But then what happens is that if I look at this beautiful spectral line, right, the Gaussian core suddenly hits the ground. And then the equivalent width grows only very slowly with increasing optical depth. Right? In fact, it grows in proportion to the logarithm of tau 0 here. This is because we have this exponential in the Gaussian shape. And then finally, if the line becomes stronger and stronger, even the Lorentzian wings hit the ground of the spectrum. And then the curve starts growing like 1 over the square root of tau 0. So that's a very characteristic shape. Now, what can you do with it? If you have only a single line, you can do nothing with it. Because there is still the degeneracy in tau 0 between the number of absorbers and the optical and the geometrical depth of the gas distribution. However, suppose you have two lines available of the same gas distribution, then the oscillator strengths are typically different. Then you have two curves of growth, of which you know that the number of absorbers and the geometrical width should be the same, but the oscillator strength will be different, and therefore you will hit these two so-called curves of growth for these two spectral lines at different points. And then you can break the degeneracy in tau 0 between the number of absorbers and the geometrical width of the gas distribution. So therefore, what people typically do is they look, for example, at different spectral lines of the same element in one gas cloud or of different elements. Then they will see at what point in the curve of growth they are, given the oscillator strength of that particular line. And then once you have 2 or 3 or more measurements, you can constrain not only the product of the number density of the absorbers and the geometrical depth, but you can separate the two and break the degeneracy between them. All right, that's what I wanted to show you. If somebody asks you what is a curve of growth, Well, please. It is the integral over 1 minus the exponential of the optical depth if you insert into the optical depth the Vogt profile. So far, so good. Do you have questions? It may happen that somebody asks you to analyze a spectral line or more of them. All right, so with that, I wanted to conclude the section on radiation processes in astrophysics. Remember, we did not do very much. We, first of all, started from Larmore's equation. We used that to derive, together with Plancherel's identity, a general algorithm for calculating a spectrum, and we used that to calculate the spectrum of synchrotron radiation and of Bremsstrahlung, thermal Bremsstrahlung. Then we moved on to study the energy exchange between charges and photons, where we needed the process of Compton scattering, wherefore we gradually moved away from treating electromagnetic radiation as a Maxwellian field to a collection of photons. And then finally we looked at quantum radiation transitions to see what we can learn from spectral lines and how we can understand spectral lines. Now on the problem sheet you will find a problem that uses all of these results in order to calculate the bound-free cross-section for hydrogen. Right? What is the cross-section for ionizing a hydrogen atom away from its ground state? And you will find exactly the same problem in the book. Almost. Good. Okay, so far so good. No questions? If there are no questions, I will have questions, but I told you before. So then we will move to hydrodynamics. And the goal of what I'm going to say now is, first of all, how do you justify ideal hydrodynamics? And second, what is the difference between a gas and a fluid? What is the difference between a gas and a fluid? And we will see. We'll see about that. Okay, and then of course we will have to derive equations of motion for a fluid. So, remember this lecture has 4 parts, right? Radiation processes, hydrodynamics, plasma physics, and magnetohydrodynamics. A little bit of stellar dynamics adds to it. So then we are now at hydrodynamics. And I will start justifying or outlining the foundations of hydrodynamics in a relativistically invariant way. For a certain purpose, I wanted to highlight, without using it, the point where you can depart from special relativistic hydrodynamics to general relativistic hydrodynamics. I won't go that way, but I wanted to illustrate the only change that you have to make in order to arrive at equations of generally relativistic hydrodynamics. So I will start with relativistic formulation, and for that I will span a phase space with 4-dimensional positions and momenta. This is not very different from the generalized phase space that you know, that has time, position, and three-dimensional momentum. There's just one component more, right? Because time is x0, position is x1 to 3. So the only dependence that we have added in addition to the generalized phase space that you know is the dependence on P0, the energy. This is redundant. This is redundant. We don't need that, right? Because we have an energy-momentum relation. So once you know the rest energy and the 3 momentum, you do know the fourth component of the momentum as well. So there's a redundancy in between, but nonetheless, we start from that. Because I now want to integrate this over d4x and d4p. The reason why I want to integrate this over d4x and d4p is that d4x and d4p, the 4-dimensional volume elements of that phase space, are Lorentz invariants. The reason is that Lorentz transformations have unit determinant. Okay? But what is this, right? If this is the phase space distribution of particles, then the meaning of F tilde is, if I look at the position x mu and p mu in phase space, how many particles do I find there? So the meaning of F tilde is supposed to be the number density of particles in this extended phase space here. If I integrate therefore over d4x and d4p, that must be the total number of particles that there are. All right, so this means that we have a Lorentz invariant on the right side, we have a Lorentz invariant, we must have a Lorentz invariant on the left side. Since d4x and d4p are Lorentz invariants, F tilde must be a Lorentz invariant itself. Okay? Now I'm going to integrate out the redundancy. So I want to do this operation now. Under the constraint of the energy momentum relation. Let me write it this way. So in other words, I want to integrate now over the momentum, the volume in momentum space, taking into account that there is an energy momentum relation that I have to satisfy. Those of you who have already had contact with quantum field theory, that's what you call the on-shell condition in quantum field theory, right? Okay, I just want to do this because I want to show you one thing. This contains, this is not p to the power of O2, right? This is p0 to the power of 2. Now it's correct. All right. So now I can use this argument of the delta distribution here to integrate out the P0. In other words, I can use that in order to make sure that all the particles that I'm now considering satisfy the relativistic energy momentum condition. So I want to integrate out dP0, but then I have to take into account that this delta distribution depends on P0 squared. So I have the situation where I want to integrate a delta distribution of a function of x, which I can write in this way, right? So what does this mean? I first of all have to find out all the roots of f. Those are the xi. Then I have to multiply the delta function that is now left as a delta function of the unchanged argument x. I have to multiply this by 1 over the absolute value of the derivative of the function f at its roots. So I can write this as, now this is square in P0, so I get two solutions. I take only the positive solution of that. This is 1 over P0 delta D of P0 minus, let me just call this E over C, right? The zero component of the momentum must now satisfy energy over C. Okay. The only thing I want to point out is there is now a factor of 1 over P0 appearing. And then I can write this integral as d3p divided by P0 times F tilde arguments. And now in this distribution F tilde, I can replace the zero component of the momentum by the energy divided by C. This is the main point. I have now modified the relativistically invariant four-dimensional momentum volume element by a three-dimensional volume element divided by the energy. And what we said about relativistic invariance before means that now we see that d3p over the energy is also Lorentz invariant. Okay? So the result of that consideration here is that d3p divided by the energy is also Lorentz invariant here. That's the main point, and this is the reason why in all what we are going to do now, an integral over d3p will occur, but divided by the energy in order to make this three-dimensional momentum volume element also Lorentz invariant. And again, you may recall the calculations in quantum field theory where you see d3k divided by omega, for example, and it has exactly the same reason. And you have the on-shell condition, and because you have that, you arrive at these specific energy-weighted three-dimensional volume or K-space integrals. That's all. Right? Now we go to we go away from the F tilde here. So now I'm going to introduce a phase-based distribution which is now parameterized in the usual way by T, X, and P. Right? This is by the time, or x0, the three-dimensional position x, and the three-dimensional momentum p. And again, this phase-based distribution here is the number of particles, or the particle number density on this extended phase space. All right. Particle number density on phase space. But this means that once I integrate over d3p over f, I must get the spatial number density. And now I introduce a notation by this relation here. So I use f as a probability distribution. So I have to normalize f times the integral of f times a quantity q, whose average I want to know, by the integral over d3p over f. But this is the density. So therefore, this relation here just defines the ordinary average if you take the normalization into account. But remember, integrals like that here, integrals over d3p f times q, are not just averages, but averages times the spatial number density. Okay, that's what we need. And now I'm going to introduce two things, two objects, just for the fun of it. And you will see we will have a lot of fun with them. They are going to be 4 vectors and 4 tensors. Right? So the first thing is going to have 4 components. The second thing is going to have 16 components. And I'm defining this as c times the integral d3p over e f times p alpha. So I multiply the phase-space distribution f by all components of the 4 momentum, and I integrate over our relativistically invariant volume element in momentum space. And T alpha beta goes just like that, except that now I take 2 factors of P. Okay? Yes, that's what we do. This is nice. Before we see what that means, let me write down the following relations. The 4 momentum P mu, written as a 4 vector, is this quantity here. It has the 0 component gamma mc, and it has the spatial components gamma mv. I'm going to write the velocity v here as x dot because I will need the velocity v for something else later on. Okay, so that's the 4 momentum here. And at the same time, I know, of course, that the energy is gamma mc squared. So I can eliminate the gamma m from both. And I can write the momentum also as E over c squared times cx dot. Right? That's just equivalent. And we will use both ways of writing the momentum 4 vector. Okay. So now I'm returning to the 4 vector capital J. And this is going to be and now I'm going to use this way of writing the entire the entire 4 vector for the momentum. Right? So you see, first of all, the E cancels, the C almost cancels. Then what remains is 1 C x dot times F. So you see the 0 component is just given by the integral d3p over f. That's the particle spatial number density n. And here I have an integral of exactly that type. Right? It's an integral over d3p f times some quantity. The quantity is x dot. So this is going to be So now we have all four components of this 4-vector J in one step. And I'm going to write it as, this is 1 over C, sorry, n over C times CV, Cx dot. This is an n. All right. That's the vector J, just written in a different way. And in that way, we are going to use it later on. But now it's time for your quiz. And for me, it's time for wiping the board. So please go, not away, but on the lecture website. Find the online test and do the quiz. You should find the quiz, first of all, you should find 5 questions. Please answer them. And don't be afraid of anything. Just let me know where you are. All right. Are you done? All right. Since I stole your break, let's have another 5 minutes break. And then we continue at 10:10. Seems that you are back anyway. Can we move on? Of course, I know that I should ask those that are not here, but how am I going to do this? All right, I've collected here some expressions that we had before. Remember these two things here, J and capital J and capital, yes. Sorry? Somebody outside. Let me slowly move on. All right. So remember that capital J and capital T are definitions of objects that we may or may not find useful. And the evaluation of the capital J led to this 4 vector here, the common prefactor n over c, and then the 4 components c and x dot. Now I've rewritten this tensor t here in this way using the tensor product, just because the notation becomes less clumsy then, understanding that the alpha beta component of this tensor product are just given by the alpha component times the beta component. All right, now what happens if I use this definition here and now write the first factor p here in that way and the second factor p in that way? Okay, just for the fun of it. Then you see, if I use this expression for the first factor, the e over c squared just cancels. And I can write this as integral d3p. Now what remains is the factor gamma m. So gamma m f. Now cx dot tensor product with cx dot. Okay, now I can just pick out the corresponding components. See, now all the quantities that remain are averages over certain quantities. And let me write them in the following way. If I take the 0, 0 component, I just get a factor of c squared. That's constant, of course. I'm assuming that the particle mass is also constant. And then I have an integral over d3p of gamma times f, which is n times the average of gamma. So I have c squared m average of gamma times n. Now the product of particle mass and particle number density occurs, and this is of course the particle, the mass density of the particles. All right, so that's the 0, 0 component, and let me write this right away in the following way. This is rho average of gamma times c squared, right? The rho is the n times m, and the c squared remains. All right, now let me take the factor c times x dot. That would be the top right, the 3 top right components of this tensor here. Then there's a factor mc that is constant that I can pull out the integral. There's a factor gamma x dot that's averaged over f. So that gives me an n gamma x dot average. So this is c times n m n gamma x dot. And again, this is just the density here. Now I must write this as a transpose vector here because now it's a line vector at the top right. The same factor must appear here because that tensor is by construction symmetric. Now what remains over here is just a rho times gamma x dot x dot. So this is the 3x3 block in the spatial part of this tensor. Need to see what to do with that. And here we have these expressions. Now, in order to see what they mean, let us make a non-relativistic approximation. Non-relativistic approximation. So then I can write this is approximately the average of 1 plus beta squared over 2. Do you see that? In gamma is 1 over the square root of 1 minus beta squared. In the non-relativistic approximation, beta is a small number. So then 1 over the square root of 1 minus something small is approximately 1 plus a half because of the square root, the small thing. Right? All right, so now the average of 1 is of course 1, and then you have 1/2. Now let me write the beta square as x dot square average divided by c squared. Okay, beta is the, or beta square is the velocity square divided by c squared, and so I can write the velocity like that. Okay. Then I need this object here. That's this expression. So first of all, I get an average velocity now. Right? If I multiply 1 times x dot, an average, and the average velocity I'm abbreviating by v. That's what I needed the symbol v for. Okay. And then I need to take the average of x dot squared times x dot divided by 2c squared. Okay. And in the non-relativistic approximation, you see we are multiplying here the velocity square, which is small compared to the speed of light, times the velocity square, which would be of order of the 4th power, at lowest order in the deviation from 1, so that I ignore the gamma over there and approximate the x dot times gamma by x dot times x dot. Ignoring, well, taking into account terms of 3rd order in the velocity, but not terms of 4th order. Okay, let me return to t now. In the non-relativistic approximation, therefore, I'm getting here rho c squared to lowest order. This is, of course, just the rest energy density. Then I get rho times c squared times this expression divided by 2c squared. So that's plus rho over 2 x dot square averaged. This is the kinetic energy density, right? I mean, mass divided by 2 times velocity squared, that would be kinetic energy. So this is the kinetic energy density. What I have here in the 0,0 component is just the rest energy density and the kinetic energy density stored in this system. That makes a lot of sense, I think. All right, what do we have over here? There's a factor rho c, and then we need to multiply this with that quantity here. So this is rho cv. Okay. Rho c squared, no, sorry, rho c times this is plus 1 over c, rho divided by 2, x dot squared times x dot. this is the current density of the kinetic energy, right? Rho times x dot squared is the kinetic energy. This is transported with x dot. Right? That's a current of kinetic energy. And since the density appears there, it's a current density of the kinetic energy. These vectors are transposed. Here we have the same ones because of symmetry. All right, and the rest I just leave. And write it like that. All right, so if I introduce a further quantity, small q vector, three-dimensional vector, as rho over 2 x dot squared times x dot. That is the current density of the kinetic energy. Current density of kinetic energy. And with that, I can write this non-relativistic approximation of the energy momentum tensor of this tensor T in that way. So what does this mean now? Well, here is the sum of two energy densities, the rest energy density and the kinetic energy density. Here is the sum of two current densities. That's the current density of the rest energy, and that's the current density of the kinetic energy. And this is something else. Now, let us have a further look at the velocity x dot and the velocity v. So x dot is the velocity of a single particle. If I average this over sufficiently many particles, I'm getting an average velocity v. No, let me write it like this. And this average velocity v is perturbed by each particle by a peculiar velocity u. So what I'm imagining is I'm having a number of particles, let's say 1022, and they all move in a microscopic fashion. Now I average over them, and I get a mean velocity of them as an ensemble. And about this mean velocity, all these particles would jitter a bit. Now, if I define in this way v as the average of x dot, then of course the average of u must be 0. All right, now let's return with that splitting of the velocity x dot into a mean velocity of a particle ensemble and the velocity perturbation or velocity fluctuations about this mean velocity. Let's insert this again into the components of this tensor capital T. So what I need are, first of all, expressions like that. X dot vector squared. Now this is by definition this average here. Now every term where u appears only in linear way, is going to disappear. So what remains is only, v squared plus the average of u squared. And the mixed term is going to drop out. Let me now look at the next term we need. That's the average of x dot squared times x dot. This average here. Okay, this is now the average of u squared plus v squared plus 2uv. Now I need to keep it, because it will be multiplied in one instance with another u. And then I have a square of u, which does not vanish anymore. So this is the square now times u plus v average. Okay, u squared is going to be a scalar. U is a vector. The vector cannot have a preferred direction because we average it out. So this term, average of u squared times u, is going to drop out. Bye-bye. Next term, u squared times v, can be written in this way because v is already an average. So now I've taken this and that into account. Now I have v squared times u, that's going to vanish, right? Because again, an average over u is going to appear. And then we have plus v squared times v. That's this term. Then we have an interesting term here. That's 2 times u times v times u averaged. And I'm going to write this in the following way. 2 times u vector u average times v. You see, that's exactly the same thing, right? Because if I multiply this tensor now, u tensor product u with v, these two reproduce that scalar product, and this factor u gives that one. But in this way, I can write the two quantities that I have to average over in a separate way. All right, so now I'm done. And finally, I need this average over x dot times x dot. And by the same logic as before, this is v times v plus average over u times u. Right? Again, the mixed product that should occur is going to drop out because the average of u is 0. All right, so now we have these expressions here. Now, I can write the tensor T again as rho c squared plus rho over 2 times this, right? So I have plus rho over 2 times v squared. Then I have rho over 2 times u squared. This is the ordered velocity, right? This is what remains of the particle velocities once I have averaged over many of them. So this is an ordered part of the kinetic energy. This is then an unordered part of the kinetic energy. What is an unordered part of kinetic energy? Heat. Heat, right? This is thermal energy content. Okay, so that's the internal, that's the energy density now. Let me move on now with the other components here. So I have rho CVT, that doesn't change anymore. Then I'm going to copy 1 over c times q, because q is going to be a lengthy expression that I'd rather leave outside. And here we now have rho of V times V plus rho times U times U. All right, and we move on, because now, as we said, rho divided by 2 times the average of U squared. This is the unordered kinetic energy density. This I call epsilon. And by the equipartition theorem of thermodynamics, you know that this is 3/2 n kBt. That links this part of the kinetic energy density to the temperature. And the density temperature and the density of the gas. Look, I've written 3/2 here. This makes an assumption. The equipartition theorem only tells you that each degree of freedom gets kBt over 2 in thermal energy. So I've assumed that each particle has 3 degrees of freedom, as point-like particles would have if they only have the degrees of freedom of translation. This doesn't need to be. You could have, for example, rotational, vibrational degrees of freedom. You could have particles that consist of particles that are molecules, right, that could vibrate against each other, and so on and so forth, right? So this is for sure. This makes an assumption that we have point-like particles here. If we had any internal degrees of freedom that could be excited, we would have to change the factor of 3 here. Okay, in addition, I will have a look at this here. And well, now U times U is the tensor product of the unordered velocity with itself. The unordered velocity must not have a particular direction, because it should be isotropic about the average velocity. If that is the case, then this must be proportional to the unit matrix. Okay? And I call the proportionality factor the pressure. So this is just the pressure times the unit matrix here. Okay? Suppose you had a magnetized plasma or something. Those velocities could well retain an order, a preferred direction. Then we would have a deviation from the unit matrix here, and then we would have to distinguish pressure components in different directions. There could be a pressure component along the magnetic field lines, could be a pressure component perpendicular to the magnetic field lines, right? I do not want to introduce complications here, but I'm just mentioning we are making assumptions here. And in specific situations, they may or may not be satisfied. Right? And then you should go back here and change things. All right, finally, Q, this is the vector rho over 2, x dot square times x dot square times x. Okay, then I have U square average times V. Here you see rho half divided, rho half times U square average. This is again the heat, right? It's the internal energy density, which is flowing here with the velocity V. Well, that is very intuitive. Okay, next term is going to be rho V squared times rho half V squared times V. That's the flow of ordered kinetic energy. Right? So we are just splitting this vector up into a flow of heat, a flow of internal energy, I should say, and a flow of ordered kinetic energy. But we have another term, and this is plus rho times v. And again, this tensor u times u. So this is PV times, rho times this is the pressure times the unit matrix. Unit matrix times V gives the velocity itself, right? So this is just pressure times velocity here. Yeah. That's true. That's true. If I want to write rho here, I should divide by the particle mass, yes. Thank you. Okay, so you see, you can write this, this kinetic energy current density, Q, as rho times V squared times V divided by 2. Then rho half U square average, that's epsilon, plus P, and all multiplied with the velocity. All right, so again, I can return to the tensor T here and write, this is rho C squared plus rho half times V squared plus epsilon. So in other words, the energy density consists of the rest energy density, the ordered kinetic energy density, and the internal energy density. Then here we have rho C let me write it like that, and it becomes even more obvious. Rho C times V, of course, but that's going to follow. And then all of that plus the pressure times the velocity. Look, this is almost the kinetic, the total energy density flowing, but a little bit else, right? A little bit more. Why is that? We have to see about that. So all I want to point out right now is this additional pressure does not appear here. And there's a good reason for that. It appears in the flowing term, but not in the resting term. Okay, what else? We have rho times V tensor V plus pressure times the unit matrix. And this part of the tensor is just given by symmetry. All right. Very important. Now we have the two objects, right? We are still talking about capital J and capital T. The capital J turned out to be what? Its zero component is just given by the number density of the particles. Its spatial component is given by the flow of these particles, right? Wait a moment. I took an average there because I integrated over the phase-based distribution. So that should be an average. So this is N over C, CV, right? To use the same notation as down here. Then we had a look at this object capital T, for which we first introduced the relativistic definition. Of course, we could return to this relativistic definition if we had to do with the relativistic flow. Or if we had to do with general relativity, could be, right? Once in your life this may happen. in order to see what the components of this object T mean, however, we made a non-relativistic approximation. In this non-relativistic approximation, we identified, or we separated ordered motion from unordered motion, identified the unordered motion with internal energy and pressure, these things, right? And identified the components of the tensor otherwise. That's the energy momentum tensor, capital T, and the capital J is, sorry, is the current density of the matter. All right, now what do we do with that? And now comes the decisive step. The decisive step of all of hydrodynamics, right? So far we have just introduced quantities and split them in a nice way. We took care that they are relativistically invariant in their definition and so on and so forth. All right, but we just defined J and T and looked at the components of these things. Okay, fine, but now the physical essence is the following. If I take this phase-space distribution and look at its total time derivative, Liouville's theorem of classical mechanics tells me that this is zero. Wait a moment. This is zero under Hamiltonian dynamics. Okay? Why is that so? The only condition that you require for Liouville's theorem to hold is that the underlying dynamics is symplectic. That's the little minus sign in the Hamiltonian equations, right? That you have in one component, not in the other. This is the symplectic structure, or that's it's a manifestation of the symplectic structure, and because this symplectic structure holds, therefore Liouville's theorem holds. There's almost no way around Liouville's theorem. What does this mean? This means that the partial derivative of f plus the gradient with respect to x times x dot plus the gradient with respect to p times p dot equals 0. Okay, I want to look at a situation in which I have no external forces, in which case p dot would be 0. So, of course, if I want to later include external forces again, I will have to reintroduce them, but for now I'm excluding them. So then, Liouville's equation means, and now I'm dropping the subscript x of the gradient because now it retains its original meaning again. So that's Liouville's theorem. All you need is the symplectic structure of the Hamiltonian equations. Okay, but then what about non-Hamiltonian dynamics? What if the particles collide? Then they will interact in a way that does not need to be controlled by Hamiltonian dynamics. So generally, I will have to modify this equation by collision terms on the right-hand side. And these collision terms may depend, and will generally depend, on the phase-space distribution itself. So they are a functional of the phase-space distribution. For example, you could in this way arrive at Boltzmann's equation if you make a certain assumption about the collision term. Right? Then you have a dilute gas and the collisions are just given by two-body collisions. Then you arrive at the Boltzmann equation. But you could have three-body, four-body, and so on collisions. You could have particle correlations on the right-hand side and whatnot. Right? So you can have, this gives rise to arbitrarily complex equations of motion for the phase-space density. And among them, the Boltzmann equation is, so to speak, the lowest order. That takes collisions into account. But now comes the decisive part of hydrodynamics. It consists in two steps. The first step is to realize that there is a scale hierarchy in hydrodynamics. There's a microscopic scale where the individual particles are living. There's a mesoscopic scale which tells you about variations way above the microscopic scale. And there's a macroscopic scale, which is the overall dimension of the system you have in mind. So I have three scales. I have a scale lambda, that's the microscopic scale. I have a scale L, the mesoscopic scale. I have a scale capital L, that's the macroscopic scale. Think of a swimming pool. Right? It's about the right time of the year. L would be the dimension of the pool itself. Small l would be the dimension of the little rubber duck that you want to take with you into the swimming pool. Lambda is the scale that characterizes the separation of the individual molecules. And there's a very clear scale separation here, which says that. Now, what we are doing when we are averaging, like we did before, is that we are averaging over scales which are large compared to lambda but small compared to L. And if we have a scale hierarchy like that, then this is possible. And this doesn't need to be the case. Right? So the first decisive step in the development of hydrodynamics is to recognize I have a scale hierarchy. Like that. And the swimming pool is one example, but of course a galaxy cluster is another one. Right? The microscopic scale is the mean separation from one particle to the other. This is really small. It's still on the order of maybe 10 centimeters, right? But it's very small compared to everything you want to know about the galaxy cluster. There's a mesoscopic scale, which could be the scale of individual galaxies in that galaxy cluster. And there is a macroscopic scale, which tells you something about the whole thing. So this is why, for example, you can apply hydrodynamics even to dilute gases, if you can ensure this kind of scale hierarchy. So that is number one. Number two is, if I take a momentum integral over the collision term, or a momentum integral over the collision term times the momentum itself, then both are zero. And this does not mean that no collisions are happening. But this means that collisions are so frequent that if I integrate over the mesoscopic scale, there is no net change of these quantities within mesoscopic volumes. In other words, this tells you here that collisions are so frequent that on average, no particles escape from the mesoscopic volumes or no particles enter it as a net effect. Right? In other words, the scale hierarchy ensures that if I integrate over the mesoscopic scale, particle number is conserved. Just because there are so many particles kicked out of the volume and so many particles kicked in that on average there's no change. This here means that there is also no energy exchange and no momentum exchange. Right? Collisions are so frequent that there is, on a mesoscopic scale, no exchange of energy and momentum from the volumes. Yes?
Sorry to bother, why can we see that it is specifically the mesoscopic scale and not, for example, the microscopic?
This is what we define here. So these integrals here are defined to be on a mesoscopic scale. All right, these are the two main ingredients, right? You have a scale hierarchy. Number one, if you don't, stop applying hydrodynamics, please. There's such a lot of nonsense being made in cosmology, for example, assuming that there is a scale hierarchy while there isn't. Okay, so number one, scale hierarchy. If you can be sure that there is one, go ahead. Number two, there are collisional invariants on a mesoscopic scale. And these collisional invariants that we have identified here are the particle number, the particle energy, and the particle momentum. Certainly not of each individual particle, but averaged over very many particles on a mesoscopic scale. Okay? So these two things, right? You have a scale hierarchy and you have collisional invariants. They are at the foundation of hydrodynamics. And this means that the hydrodynamical equations allow you to lift microscopic conservation laws on the mesoscopic scale. And then the hydrodynamical equations are just conservation equations, no more than that. But the existence of that scale hierarchy and the existence of the collisional invariants on the microscopic level allow you to lift the collisional invariants to the mesoscopic level and therefore to quantities that we can deal with. Okay? So the initial question was, when we started about hydrodynamics, was what distinguishes a fluid from a gas? You may have collisional invariants in a gas as well. Usually you do. But you have no scale hierarchy because the mean free path between the particles is so long in a gas in comparison to a fluid. And if you make ideal hydrodynamics, right, if you hear the term ideal hydrodynamics, it's the limit of infinitely small microscopic length scale lambda or infinitely small mean free path of the particles. Now, of course, infinitely small, as always if you use this term in physics, is an approximation, is an idealization. It means very small compared to all other scales you have available. That's the key point. Okay? Then, if you want to move from ideal hydrodynamics to, let's say, viscous hydrodynamics, you make the mean free path a little larger. You make it a little larger than infinitely small. And then you get transport effects, right? And one of the transport effects is heat conduction. One of the transport effects is viscosity. That's momentum transport, and so on and so forth, right? So that's the key point. If anyone asks you what's the difference between a fluid and a gas, it's the mean free path. For a fluid, it's very small. For an ideal fluid, it's infinitely small. For a non-ideal fluid, it's small but not infinitely small. Okay? And from that, with these objects that we now have, right, J and T, you can imagine now what happens, right? We will derive conservation laws for J and T. And these conservation laws will always look the same, right? They will look like that. And this is what we are going to derive on Wednesday. Starting from this equation here, right, we will see that the covariant four divergences of these objects are going to vanish. And this will allow us then to derive the hydrodynamic equations. If you wanted to go to general relativistic hydrodynamics, you replace the partial derivative by a covariant derivative and happily move on. All right? See you on Wednesday.